Today we want to talk about electron configurations. Now, what is an electron configuration? Basically, it's a way of denoting or writing where all the electrons are in the atom in terms of their energy states, and so on. And you've seen these in some of the previous videos we've looked at. So we want to look at how to write these. First of all, you've seen something like this before, so let's just kind of break this down and look at what these numbers mean. This number here, the 1, is the principal energy level. It's the principal energy level. The S is the sublevel. And the superscript 2 is the total number of electrons in that sublevel. Okay, now let's see how this works. We've already gone through the breakdown of principal energy levels, sublevels, orbitals, and spin, and how each electron in an atom has a certain set of properties, and no two electrons in an atom can have the same principal energy level, sublevel, orbital, and spin at the same time. So let's say what we're going to do here is we're going to call this we're going to build an atom from scratch and see how the electrons would go into that atom. And what we're going to be drawing here is an orbital filling diagram. Sometimes called an off-bow diagram, because it uses something called the off-bow principle. The off-bow principle is simply that electrons will spontaneously or automatically go to the lowest available energy position in an atom. They'll go to the lowest available energy position in an atom. So let's say we wanted to make hydrogen. I'm going to start down here, and what I'm going to do is I'm going to show hydrogen. Hydrogen only has one electron, and what it's going to do is it's going to go into the first energy level, and of course the first energy level where n is equal to 1, only has one sublevel, and that's S, and that sublevel only has one orbital. Okay, so the single orbital we call a 1s orbital, and we signify it with parentheses. So the parentheses here represent the orbital. And the electron we're going to represent with an arrow, in this case representing a spin up electron. So the arrow represents an electron, in this case with spin up. That would be hydrogen. Now if we wanted to change this into helium, which has atomic number 2, so in the neutral helium atom it has 2 electrons, all we would have to do is add another electron in that orbital. And that would be a picture of helium, or that would be an orbital filling diagram for helium. Now, let's take a step back a second, back to hydrogen. There's another way of writing this. So you can draw it as the orbital filling diagram here, or you can write it in a kind of shorthand, which would be 1s1. So what we're saying here is we're in the first energy level, we're in the S sublevel, and there is one electron in that sublevel. And so the electron configuration is 1s1 for hydrogen. If I had helium, then my electron configuration would be 1s2, because I now have 2 electrons in that orbital. They're represented by these 2 arrows. Now what if we wanted to make lithium? So we're going to change this to lithium. Well, lithium has another electron, but I can't put another electron in this orbital, because then that third electron would have the same, since there's only 2 options for spin, up and down, that third electron would have the same principal energy level, sublevel, orbital, and spin as one of the other electrons, and it would violate what's called the Pauli exclusion principle, that no 2 electrons in an atom can have the same 4 properties. So what I have to do is go up to the next energy level 2, and put an electron in the first sublevel of that energy level. So that would be lithium. Now lithium's electron configuration then, written like this, would be 1s2, 2s, 1. So there's 1 electron in the 2s sublevel. If I want to make beryllium with 4 electrons, then I just add another there, and I add another there. The next atom would be boron. Boron has 5 electrons, but as we can see, we can't put any more in the 2s. Well, what would be next? If you remember the sublevels have energies that work like this. The S sublevel has less energy than the P sublevel, which has less energy than the D sublevel, which has less energy than the F sublevel. So what we're going to do is, after the S, we're going to go into the 2P sublevel. And I'm going to draw an offset here just to make it clearer, a little bit clearer what's going on. This is the P sublevel in the second principal energy level. So down below this line is the first principal energy level, and below this line is the second principal energy level. So for boron, if I want to have 5 electrons, I just put one in the first p orbital. You might say this is the p sub x, and then this would be the p sub y and the p sub z, but we don't need to label those on here. So what would happen if I wanted to make carbon? Oh, by the way, this would look like this, 2p1. That would be for boron. 1s2, 2s2, 2p1. If I want to make carbon, I've got 1 more electron. And you can see here, hopefully, that it's going to go into the 2p sublevel. But it's a little bit tricky because it turns out I can't put it in the first orbital. I have to put it in the second one like this. And that is something that's called Hund's rule. And Hund's rule states that electrons don't pair up in an orbital until all orbitals have been occupied. I guess an easy way to think about this is just that electrons don't like to pair up in the same orbital. So what they'll do is they'll spread out across all the orbitals in a given sublevel first before they start to pair up. So let's finish this here. This would be carbon, 1s2, 2s2, 2p2. And then if I move on to nitrogen, that would be 1s2, 2s2, 2p3, and I just put another electron like this. Now when I move on to oxygen, and this would be 2p4, 4 electrons in the second p sublevel, then I would start to double them up like this. And that obeys Hund's rule because I've already put 1 electron in each of the 3 orbitals, and so I can now start doubling them up like that. Alright, and that would be oxygen. And then if we go to fluorine, we would see this. Alright, and notice there's 1 empty space in this second energy level, the p sublevel, 2p sublevel, that would be fluorine. And then when I go to neon, I would fill up that p sublevel, and it would look like this. Okay, so that would be, this would be neon's electron configuration, and this would be neon's orbital filling diagram. Okay. Okay, so let's see what would happen if I move on to sodium. If I move on to sodium, you can see that I can't put it in the 2p, and I can't start a 2d because the second principal energy level does not have a d sublevel. So what I'm going to have to do is go into the third principal energy level and start there. So that electron, that additional electron for sodium now, which has a total of 11 electrons, is going to go in there like that. And what I'm going to do in this configuration notation here is I'm going to write a 3s1 like that. Okay. Now if I want to make magnesium, I'm going to add one more electron here, and I'm going to add one more electron here. If I want to make aluminum, then I'm going to start the 3p sublevel like this. Okay. Okay, that's aluminum, and aluminum has 3p1 as the end of its electron configuration. If I want to make silicon, I just change this. Okay. Now I'm gonna skip a couple here. So that would be silicon. This would be phosphorus. Okay, and this would be sulfur, and then chlorine, and then argon. All right. Now I want you to notice something though at this point. This would be argon right here. And I hope that you can see the relationship between argon and neon. Remember that with neon, we ended with this as the outermost sublevel. And now and it was full. It was a full 2p sublevel, a full p sublevel. With argon, we end up with another full p sublevel as our outermost or our highest energy level sublevel. Okay, so with the noble gases, that's what we're expecting. We're expecting, and by the way, they also have 8 electrons in the outermost shell. So this one has 8 electrons in the third shell, the third principal energy level, and this one has this one had 8 electrons, or neon had 8 electrons in the second shell, which was its outermost principal energy level. That's argon. And so argon would look like this, 3p6 on this here. If I wanted to make potassium, which would have one more electron, you might think that I'm going to open up the 3d, and that would make sense because we know that the third principal energy level does indeed have a d sublevel. But it turns out that the 4s sublevel, fourth principal energy level, s sublevel, actually has a little bit less energy than the 3d. So remember that a d sublevel within a given principal energy level, a d-type sublevel has more energy than a p. So what happens is there's a bit of overlap as we start to move outward in the atom to higher energy levels. We get more and more overlap as we move down the periodic table. And one thing I should do is I should note that this is what we're drawing here. This diagram has energy on this axis increasing. So energy is increasing as we go up this picture here. So my 3D's over here at a little bit higher energy than the 4s, which means that potassium would look like this instead of having an electron in the 3D. So it would be 4s1. That would be potassium. And then calcium, would be 4s2, and it would have 2 arrows in the 4s. We wouldn't start putting any in the D until we got to the next element, scandium. that would be 3d1, like this. When we go to titanium, we would have 3d2. Now notice how I'm following Hund's rule here. I'm not pairing them up in the 3d sublevel until I've spread them out all the way across. Let's keep moving. We're going to go to vanadium. And don't worry, I'm not going to go through the whole periodic table here. It's 3d3. And then to chromium. Alright, sorry, I forgot to put vanadium in there. So chromium we would expect would look like this. Now, this is what we would expect for chromium, according to the rules we've been following so far. But it turns out that because the 4s and the 3d are really so close to each other, and because of the fact that, I guess it lowers the energy of the system if we half fill all of the sublevels like this. So what happens then is in chromium, this is what we would call an exception to a rule. So for chromium, we actually get something that looks like this, where you have a half-filled 4s and a half-filled 3d. One electron in each of the 5 d orbitals in the third principal energy level. So that's an exception to the rule, and what would that look like in the configuration here? It would be 4s1, 3d5. So it gives the atom a little bit lower energy when it splits them up like this, instead of having 4s2, 3d4. Now, when we move to the next element, which is manganese, then first we'll fill up that 4s. So then this would be manganese, which would have the configuration that we would expect. Alright, then iron would look like this. And that would be 3d6. Cobalt would not give us any surprises either. B7. Nickel. I'm sorry, this has nickel would look like this. 3d8. Now when we get to copper, we're going to get a little exception here again. We would expect this to be 3d9, and we would expect it to look like this with just one empty space. But what happens is this electron gets promoted. This electron gets promoted up to here, like this. Take that out of there. So this is similar to chromium. So copper is a similar situation with chromium. We get an exception. We get a promotion of a 4s electron into the 3d. And again, it's because the 4s and the 3d are actually very close in energy. And then when we go to zinc, we fill up the 4s again so that everything's full there. So that would be zinc. Move on to gallium. And now what we're going to do, because with gallium, we filled up the 3d, we filled up the 4s, so now we're going to start filling the 4p. So with gallium, which is atomic number 31, it's going to look like this. And so that would be 4p1. Germanium would be like this. Arsenic looks like this. Selenium, bromine, and krypton. Once again, when we get to the noble gas krypton, we have a full p sublevel as our outermost or highest energy sublevel. Okay, so we could continue this process, and I'm not gonna keep drawing this diagram because it gets kind of cumbersome to keep drawing the orbital filling diagram. What I'm going to do instead is show you how to continue writing it in this format, what I'm going to call the electron configuration. So if we're going to continue this process, all you really need to know is you need to know the order at which the sublevels fill, because like I said, things are going to start to overlap more and more as we continue to build this thing out. So you saw here how 4s intervened in between the 3p and the 3d, so we need to know the order. And then we're just going to, if you know the total number of electrons, and you know the order of filling, and you know the capacity of each sublevel, you can write the configuration for any element. You got to watch out for the exceptions, but the only exceptions that I'm going to require you to know are chromium and copper, so you can just memorize those. So what is the order of filling? Here's how it works. I'm going to draw what we've called the Christmas tree diagram, and I think you'll see why it's called that. 7, this is the highest principal energy level you'll have to go. So this is N, the principal energy level. And then, of course, there's an S sublevel in each one of these. There's a P sublevel in the 2P, and the second, third, fourth, fifth, sixth. Then there's a D sublevel. Here, and we have an F sublevel that we'll have to deal with in a couple of these. Now the order of filling just looks like this. You're just going to go from the 1s to the 2s. From the 2s you fill that up, and then you go to the 2p. After the 2p, now by the way, here I am, 1s, 2s, 2p. After the 2p you go to the 3s, there I am, then the 3p, there you go, and then down to the 4s, and then to the 3d. Okay? Then from the 3d you're going to go to the 4p, and there you have it. Now after the 4p it goes to the 5s, and rather than go to the 5p, it's going to go up to the 4d. After the 4d, 5p, 6s. But 6s, after 6s, you don't go to the 5d. Instead, you go up to the 4f, then the 5d, p, and s. So a p always follows a d, and an s always follows a p. And then this one, let's see, I didn't draw this very well. Let me move my little f here, because from the 7s I'm going to go up to the 5f and then the 6d. Now all you have to remember is that the s can hold 2 electrons, the p can hold 6, the d holds 10, and the f is going to hold 14. And using this you can come up with any electron configuration in the periodic table. For example, let's try tungsten, which is the symbol W, and it has 74 electrons. So its atomic number is 74. So what I'm going to do is just start writing 1s2, 2s2, 2p6, 3s2, 3p6. Now let's stop and do a little count here. What I'm going to do is I'm filling these up, so I've got 10 and 8. This is 18 so far. And now I go to 4s2, then 3d10. That's another 12, so that brings me up to 30. After 3d10, looking on my diagram here, after 3d, I go to 4p. So I've got 4p6, that's 36. After the 4p, I go to the 5s. 5s2, that's 38. After the 5s, it's the 4d. 4d10, that's 48. After the 4d, I go to 5p. 5p6, that's another 6. That brings me up to 54. After 5p6, it's 6s2, that's 56. And now I'm into the 4f. So let's see if I can move over here. I've got 4f. Now the 4f can hold 14. Alright, so let's see, 54. I better count these up again. I've got 10, 12, 18, 20, 30, 36, 38, 48, 54, 56, 70. So now I'm up to 70, and what's after the 4f is the 5d. So my last sublevel is going to be 5d with 4 electrons in it.